All right, we are now also live on LinkedIn Live and on YouTube, and welcome everybody joining us from there as well. Okay, we're just going to wait another minute to give everybody a chance to join, and then we're going to get started. Okay, we are 2 minutes past the hour, so let's get the show on the road. Again, good morning, good afternoon, and good evening, everyone, depending on where in the world you're joining us from. And welcome to this PQCA webinar with AWS about operational considerations for cryptographic migrations. My name is Tomasz, and I'm an ecosystem manager at PQCA. Now, before we get started, I would like to emphasize that everybody is welcome in our community, and we strive to create a safe and welcoming environment for everybody. So please follow our code of conduct when interacting with each other on this webinar, as well as in our broader community as well. You can find our code of conduct on our website linked here. All of the Linux Foundation webinars are held under the LF antitrust policy, and you can also find the policy on our website. This session is being recorded, and you'll be able to access the recording after the webinar on our YouTube channel, as well on our webinar playlist, along with the slides you will be able to download there as well. Now, we encourage these webinars to be interactive and engaging, and the more interaction we get, the better experience for everyone. So if you have a question, you can raise your hand, and I will unmute you, and you can speak up. And Panos will be taking the questions at the end of the session. And so you are also welcome to use the Q&A box and the chat button to ask your questions, and we will get to them as we go. Now, for those of you watching the live streams on LinkedIn Live and YouTube, please use the chat button, or I will also post the link to join this webinar live as well. So you're welcome to join us here as well. Now, without further ado, it's my pleasure to introduce Panos Kampanakis, who is a principal security engineer at AWS Cryptography. Now, Panos, over to you.
Thanks, Thomas. Let me try to share.
Yes, stopping my share. All right.
Let me see, I have to find my laser pointer. Okay, I got it. Okay, that's it. Okay. And thanks, Thomas, for the intro and welcome, folks. So today, I'm going to talk about the well-known topic of a post-quantum migration in the context of operational complexity or considerations. We're all aware of the post-quantum migration that's coming for all of us, and we're executing on it. Many folks are executing on it. But, you know, we often focus on the solutions and the concepts like cryptographic agility, migrating cryptographic libraries, and that enables us to move our software and the algorithms that we use. But today I wanted to focus more on pain points, on some pain points that have to do with legacy software that needs to be supported for a long time, or complexity, application complexity and architectural complexity. So some of these problems, I would not say they have elegant solutions. Sometimes they're complex issues that, you know, we have to work through, and you know, they're not always easily solvable. But I wanted to bring them up here in this context, since we have been focusing on the migration, and these are things that I've seen with some of the teams that I'm working on. My name is Panos, and I work in an organization in AWS that owns cryptography, and part of that involves post-quantum cryptography. So I work with a lot of teams, and some of these lessons or pains or challenges I'm going to share today. So the agenda has to do will cover an overview. So initially we'll talk about the problem and motivate a little bit these challenges, try to group them together, and then I'm going to break them down into two categories: long-term supported software, and then application and use case diversity and complexity. So basically, these are the main categories of challenges that I'll cover. And then in the end, I'll just summarize with some takeaways. That's my intention today. If you have any issues, I will try to keep an eye on any questions or issues to bring up. We'll try to keep an eye in the chat. Okay, so let's start by just motivating the problem a little bit and the challenges. So we all know by now what we're dealing with. We're dealing with a post-quantum migration, but more or less this topic has to do with any sort of cryptographic migration when we're introducing new algorithms for some reason. Recently, we have all been focusing on the quantum computing concern, and that's why we're executing there. So this migration, just to summarize, is motivated by the quantum computing risk. We all know that if there was a cryptographically relevant quantum computer, it would implement Shor's algorithm, and that means asymmetric cryptography could be broken. And that's a risk for data. We know of the harvest now and decrypt later attacks that, threaten confidentiality. And also there is this, the concern of impersonation or authentication types of attacks where you can impersonate or sign something by getting the private key using Shor's algorithm. So the motivation is quantum computing risk, of course. There's also a compliance motivation or a government and regulation motivation for all of us, because governments have secrets that have to live for a long time, or they are concerned that other governments are trying to break their cryptography to get their secrets. So they have motivations to get the industry to move, and that's reflected in regulations and compliance that they require from vendors. So that's a forcing factor for migrating to the new cryptographic algorithms. Industry peers have been moving, so there is motivation by the industry itself to move and protect customer data. And of course, there is a news and media element where media picks up the concern and they promote it, so customers find out about it and they ask, and it's a cycle of motivating your vendors to move. So, we all know the concern and the motivation, and there are many motivating factors here. I have a couple of examples just to show it. Here I have the NIST transition, cryptographic transition document where they say the algorithms and how long they intend to approve them for. So this is the latest draft they have. And there you go, the US NIST, the National Institute of Standards, says 2030 for ECDSA or RSA algorithms. They will deprecate them, and then 2035 they will disallow them. So this is vendors that want to comply with NIST's requirements and the FIPS requirements have to abide by that, and that's a motivating factor for migrating. Other governments are doing the same thing. France, Germany, Canada, Australia, Middle Eastern regulations. There's a lot of push, like they're putting them in their requirements to support these new algorithms. Sometimes they deviate on what exactly parameters they suggest, but more or less they're requiring a migration from all of us. The other example had to do with industry vendors. That's a recent blog post by Google where they changed their timelines for migrating. So there is a push by industry vendors to do that as well, based on academic research progress and quantum computing progress. And then, of course, I had an example here from the media picking up some of these things and amplifying them, which puts more pressure on vendors to move the needle and migrate. So that's the motivation. We're all executing, and that's the main reason here. That's why we're doing it. The risk is high, and also there's a push and need from customers and regulators. Now, how do we go about the migration? More or less, we have seen flavors of that, of strategy documents and roadmap documents about migrating. I have here some examples just in the introduction section about the topic. So here's MITRE's post-quantum roadmap that talks about a methodology of how to go about migrating. The PQ today, that's a public website that has their own process, and you can follow it and get some guidance. And there's many more, like the G7 expert group, and CISA from the US has a roadmap document. So all of these documents, they recommend to identify your cryptographic assets. You can call them inventorying or discovery or anything else we want. And after we know the assets we have, then we prioritize the important ones and we migrate. Basically, that's the summary of these methodologies. Like, you know what you have, and then you start identifying what's important, and you start executing in migrating that asset. So that's a great approach, right? I mean, more or less, we have to do some flavor of that in order to migrate our assets. But that's not always straightforward, because we don't own all these assets. Sometimes these assets we inherit from other things, depending on the use case we're working on. So these are some of the things that I want to bring up here. We have methodologies about migrating. We know that we have to migrate cryptographic libraries. We know we have to be crypto agile, but there are headaches. There are headaches that go beyond that, and I want to cover a little bit of that today. So the first set of challenges, I have them here as to give some intuition before going into detail. So the first set of challenges that I want to cover is long-lived hardware, software, or applications. Things that stay for a long time in the field, and sometimes they're hard to upgrade. These are things that we have to support for a long time, but when they went into production, you know, it was a long time ago and they didn't have an easy way of migrating. So I have here an example with hardware. We're going to talk a little bit about other things later, but just to motivate the topic here, I have these devices that are hardware devices that get deployed, and there's a car, that's a meter, and that's a base station. This is hardware that gets deployed and lives for a long time. And now here I have some code signing infrastructure that does something. It signs code that goes into these devices in some flavor or the other. And then I have a device maker that makes a piece of hardware. It could be a chip, it could be anything else. So that device maker burns in some keys, some public keys or some certificates, which are going to be used to verify firmware when it's loaded on that piece of hardware that goes on the device on the right. So the device maker burns in some stuff that lives on the hardware for a long time. Then this device goes to the manufacturer that makes the actual device, and that piece of hardware gets, loaded in or put on the hardware that makes the actual device. When the manufacturer makes that device, it also puts firmware on that piece of hardware that goes to the field, right? This is firmware that loads up the software that's going to run on the device itself. So that firmware lives on the device here and gets deployed in the field. The firmware gets signed by a public key because the hardware is supposed to verify it before it gets loaded to the CPU, let's say, to the processor or something else. So the firmware is signed at the manufacturing stage, and the keys are loaded when the device maker makes the hardware. So we have two pieces here, two moving pieces in two different parts of the process of the manufacturing process or the supply chain. Loading the hardware, loading the public keys or the certificates on the device and then signing the firmware that goes on the device. After the device lives in the field, it's pretty hard to say I'm going to update these certificates or these public keys that exist in the hardware that are burned in already. So the point that I'm making is these things have to live for a long time, and it's very hard to update them in the field with new, let's say, public keys or new algorithms. So it's not straightforward to say, I'm going to have, I'm going to update these devices. I'm going to start using new signing algorithms for the firmware. It's not straightforward to update those in the field. And that's the first set of challenges. It's legacy or things that live for a long time, hardware or software, that are painful to upgrade and they're tough to upgrade. If we're talking about an operating system, that's sometimes easier to say, I'm going to update the algorithms in the operating system at the OS layer. But at the lower layers, the firmware loading up, where it's harder to update the device, that's where the pain comes in. A good example is BIOS. Like if we want to update the BIOS in the booting process, it's not as easy to say I'm going to update the BIOS signing algorithms when I'm doing that in the field. So that's the first set of challenges, like long-term things that are hard to upgrade. Another set of challenges here, that's the second set that I'm going to cover, has to do with intricacies and complexities of the use case or the architecture. And I'm going to cover a topic that's very interesting to me, and I've spent a lot of time on it. So use case intricacies are the second set of challenges. And I'll give an example here. A good example of that is post-quantum certificates in TLS. So post-quantum certificates, we know that they're large and they increase the data that's transferred at handshake, the handshake time when you set up a TLS connection. So, that's going to affect TLS connections. The more data on the wire, about 10 or 15 kilobytes of more data means more time in the connection itself, like more time and more latency. So who's going to feel the pain of that? The web is a very good example. The web, where we load a connection with TLS, we load a page with TLS, is going to feel some pain if we say that every connection has to transfer an additional 15 kilobytes before you get the actual data, before you get the actual content on the page. So here, my friends at Cloudflare, Luke Valenta and Bas Westerban wrote a nice blog where they showed the problem. They collected some data and showed the problem. So they showed that in the connections they see for the web connections, they see small amounts of data transferred per connection. So they saw that the median, the 50th percentile of these connections, transfers 7.8 kilobytes of data. That's 8 kilobytes almost. So it means that 50% of the connections just send a little bit of data, 8 kilobytes. And they also saw that 15 or 16% almost of the connections transfer 100 kilobytes or more. So that means that most web connections are small. They don't transfer a lot of data. So the point is that if you have to spend another 15 kilobytes for connection establishment for post-quantum certificates, and your actual data is small, that's a waste, right? That you affect the connection, you affect the time that this connection takes to complete. So web connections are going to be affected. I would argue here that some of these connections do not actually show content because most web pages, they have a bunch of smaller connections that do user identification, other things like tracking ads and stuff. So these connections are small. But regardless, I don't have a big study. So, this data here shows that there's a great number of connections for the web that will be affected because they're small connections that go over slow networks sometimes for mobile connections. So they would be affected by the post-quantum certificates. So that's a use case that would suffer a lot. Now I have another use case, and that's why I'm talking about use case intricacies that uses the same type of connections, TLS connections with the same type of certificates, that will not suffer as much because of the nature of that use case. So that use case is an AWS TLS endpoint that terminates TLS connections to an AWS service. I have some data here. I call this service XYZ. I don't give it a name because AWS legal was not letting me name it. So I'm just going to call it XYZ. And I have some data about these connections that get terminated from the clients to the on the TLS endpoints in front of an AWS service. So these connections, they're mostly over 100 megabps or 1 gigabps bandwidth. So they're very fast connections. The handshakes, the median of the handshakes takes 3 milliseconds. So these are very fast connections today, the connections we see today. And they transfer sizable amounts of data, 5 kilobytes up or 10 kilobytes down. They also have a lot of requests. So they have a lot of back and forth HTTP requests just to do the REST API call to the AWS service. So 75 requests means a lot of round trips. We also, these connections, they have 1 second of total connection time. The reason is that, the client does something and then stops and calculates something else and then goes back. Sometimes the client doesn't close the connection and the connection times out. So these connections stay up for a long time. So this here means that we have very fast connections. The speeds are good. The environment is good. We transfer sizable amounts of data, and we have a lot of round trips. That means that if we added 15 kilobytes at the beginning of every connection, okay, there would be some latency, extra latency, but it wouldn't be noticeable for these applications because it's very fast. The data is sizable for the application, and because you do a lot of round trips anyway. So this is an example of the nature of two use cases being different and being affected by a post-quantum solution differently. And that's what I wanted to bring up in the second part of the presentation. I wanted to cover the uniqueness of these architectures or use cases that sometimes means different solutions affect them differently. Okay, so now we can dive into details. I think we're doing well on time. So the first challenge that I want to bring up is long-term software, hardware, or long-term support for things. And a very good example I thought was operating systems. So I'll have here a set of operating systems and what they have integrated in their distributions regarding versions of software, and hopefully introduce the problem, the complexity. So here's Amazon Linux. Amazon Linux is an operating distribution that's based on Fedora. And I have here a few versions to show the problem, hopefully. So Amazon Linux 2 is end of support next month or this month. So it's a very old version, that we shouldn't be using. And it has very old software. So it ships with OpenSSL 102K. It gets maintenance vulnerability fixes, but this is an unsupported version of OpenSSL. And of course, it will never get post-quantum algorithms for OpenSSL in Amazon Linux. So if someone wanted to get these algorithms in that distribution for their application, they could never use the native OpenSSL version coming with the distribution. The same goes with OpenSSH. So the OpenSSH that ships is 7.4, that ships with that distribution, doesn't have any post-quantum algorithms in it for SSH. So this is a good example of, okay, it's very old operating system. We shouldn't be using it, but it's still supported. Supported for another 29 days. And someone that would want to use the native versions of libraries or software on the distribution, it wouldn't be straightforward to use the native ones for post-quantum. So they would need to do additional things. Now Amazon Linux 2023 is the next version, and if you can see there, okay, if you can see in Amazon Linux 2023, it ships with OpenSSH 8.7, and OpenSSH 8.7 does not have MLChem or any other NIST algorithms. It did include Streamlight Entru, which was one of the finalists in the NIST distribution, but someone that wanted to get the MLChem and MLDSA algorithms, they would not have them in the existing version shipping with Amazon Linux 2023. With OpenSSH, it's a little different. I'm sorry, with OpenSSL, it's a little different. OpenSSL was upgraded recently to 3.5.5 in the Amazon Linux 2023 distribution, and that means that it does include MLChem and MLDSA in the library itself. So, OpenSSL native in the distribution, at least someone could integrate their applications to use MLChem and MLDSA with OpenSSL. But with OpenSSH, they would need to do something additional, either upgrade OpenSSH or, bring in some other version of OpenSSH. And the same pattern happens with other distributions. The point is that long-term supported operating system distributions have these challenges. So I have Ubuntu here just as an example. And so Ubuntu 2024. Okay, let me bring up my lighter. Okay, so Ubuntu 22.04 long-term support. It's going to be end of support in May 2027, and extended maintenance is going to be until April 2032. And then there's 24.04 long-term support for Ubuntu. End of support is May 2029, and end of maintenance is 2034. So these operating systems, they have some lifetime left in them, right? We could still be using them. Let's see what they ship with. So they both ship with 8.9, OpenSSH 8.9 and OpenSSH 9.6. If we look the algorithms they support, they have SN-true, but they don't have the NIST algorithms. They don't have MLChem and MLDSA. So you can see here, if someone wanted to say, I'm going to start using post-quantum algorithms with OpenSSH when I connect to my EC2 instance, they wouldn't be able to use these algorithms from the box, out of the box of the distribution. OpenSSL is similar. It's 3.02. So 3.02 and 3.013. So in these Ubuntu long-term supported versions of the distribution, someone could not integrate with OpenSSL 3.0, their application, to get the new algorithms. Like I couldn't write an application and build with OpenSSL 3.0 and say, I'm going to start using MLChem. These are long-term supported versions. So the point is that we have headaches when we're dealing with these long-term supported software, and we have to do manual work or additional work if we wanted to start using the new algorithms. Okay, just to bore you, I have Red Hat as well. So 9.7 LTS long-term support and 10.1 long-term support. May 2027 end of support and May 2032. And for 10.1, May 2030 and May 2035. So with Red Hat, the distributions that I checked, OpenSSH 8.7 for the 9.7 version. That means we have SN-true, but we don't have MLChem or MLDSA. For the 10.1 version, it's OpenSSH 9.9, and you can see here MLChem is there. So Red Hat 10.1, that's more recent, did ship with MLChem, at least for the MLChem version of OpenSSH. And with OpenSSL, the story is better because it's 3.5.1 for both distributions, and that means it has the MLChem and MLDSA algorithms. So again, 9.7 still has lifetime left in it, but you cannot get it for OpenSSH. And 10.1 the story is looking better. So the point is that as time goes by and the old distributions die, then the story is going to be better. But someone that wants to migrate today, let's say, and it's running some of the older distributions, has to do some work that sometimes can be complex. And that's the long-term supported software pain point. So if I want to, let's say I want to solve the problem for these older distributions, I have to bear in mind what I'm migrating for. So I could go to update OpenSSL, but API and ABI compatibility is important in these cases because applications that integrate with OpenSSL 1.1, let's say, calling these APIs, they might not work with 3.0 because the APIs change between the major versions of OpenSSL. So, if the distribution has 1.0, 1x version, 3.5 is not a straightforward migration because API and ABI compatibility. If the minor version shipping in the distribution is the one that you need to upgrade to, like to go higher, then it's more straightforward because API and ABI compatibility is, there is API, ABI compatibility in these versions. Of course, that's not, still there are so many applications calling these libraries that, it's still, it would still make me nervous to say, I'm going to remove an OpenSSL version shipping with a distribution and say, I'm going to go to my new version that I want. So what do we do? Like the point is, there's so many application dependencies for basic libraries like libcrypto or libSSL. What do I do? Do I just swap out the existing version because I want the new algorithms and declare that the new version is going to be fine for all applications that integrate with it today? So that's a great operational concern that I would have. So generally, because OpenSSL and these types of libraries have a lot of dependencies and many applications link against them, it's not straightforward to say I'm going to swap and replace. So swap and replace is usually not a good idea because we don't know what links against the library and what could break with the library. Even if the distribution has control over that, customer applications that are running in there as well may be linking against these libraries. So I think swap and replace is an operational nightmare personally, and side by side is a better option where you install the version that you want with the new algorithms that you want in a separate location, and you link against that version consciously the applications that you need and you control. I feel that operationally that's more straightforward and less error prone. So side by side and swap and replace, they're two concepts that, for important libraries like OpenSSL, etc., we need to be careful about because we could be, if we migrate blindly, it could cause a lot of pain with applications. The story is slightly different with standalone libraries. I call them standalone libraries here, or applications rather, like OpenSSH. So we have the option of swap and replace, and that means swapping the OpenSSH daemon, like we built the library and make the daemon load from the new executable. Or we can do a side-by-side option as well, where you put the new executable in a new location, and then you build a new service on top of it. So I did it here just to see how it would work. I got OpenSSH, the latest that had MLChem in it, and I built it, and I created a new service that listens on a different port. So that's the post-quantum SSH port, let's say. And then I made sure it persisted the reboot. So this is a common DevOps solution. I mean, someone could build this easily, but generally in a standalone application like OpenSSH, the pain is not as significant as fundamental libraries like libSSR or libcrypto, because there are many applications that could be linking against those. But with OpenSSH, it operates as an application, as a daemon for SSH client and server, but it's not, you don't have 1,000 applications linking against OpenSSH. So it's standalone, and it's more straightforward to say, I can build a new daemon, or at least build a new service with a new daemon. And I think that's a more straightforward operational problem. OpenSSH also carries its own algorithms, right? So if it links against OpenSSL, but it also carries MLChem if it doesn't have it from OpenSSL. So, if OpenSSH depended on OpenSSL completely for MLChem, that would be an extra pain point, because that's a dependency as well. But generally, OpenSSH as an application type of migration, I consider it more straightforward than the native libraries that are used by other applications. Okay, so we finished the long-term software challenge category, let's say. The second set, and the last one for today, is the application complexity or use case diversity. So I have some examples here, hopefully, to show the case. I wanted to summarize before we go into those how folks migrate generally. I have how AWS's approach is, but more or less many industry vendors follow similar approaches. So AWS has its own cryptographic library that's optimized for AWS's platforms. It's called AWS-LC. It verifies the code formally, the functionality formally for many of the crypto algorithms. So it's formally verified in many places. It's optimized, it's FIPS certified, and there's a lot of work and testing that goes behind it. This library allows many services at AWS to migrate or introduce new algorithms without having to do much work, because this is centrally controlled by the team that owns cryptography. The same goes for other libraries as well, like S2N TLS library for TLS, and S2N Quick for Quick, and other libraries. So these are the building blocks, basically, that enable companies or AWS or others to deploy algorithms at scale in production. So there are pipelines that pick up the changes in the algorithms in the libraries. That could be a new algorithm as well. And the pipeline deploys these new algorithms of algorithm functionality in AWS services. The service has to still expose the algorithm sometimes if it's an algorithm that they have to expose for customers. But generally, this allows us to deploy them everywhere. There's also another element, that's the client element. The client element we don't always control. So there are SDKs that AWS controls and use these libraries as well. Like there needs to be some work to integrate, to use the algorithms in the SDKs, but that's owned by AWS. But there are also clients we don't control. Like these are browsers that integrate or third-party tools. Some of these we don't control. So, others have to do work there. So when we're migrating, AWS is a little unique in a sense that there are many moving parts and work that needs to happen. So we follow the shared responsibility model in general. There are many services that are AWS's responsibility. AWS is responsible for the security of the services themselves in the infrastructure. So examples are the TLS endpoints that expose the service APIs, or it could be the VPN service, or it could be the CloudFront service for content delivered. So these services get migrated transparently, and it's AWS's responsibility, and you're done. There are also elements, though, where the customer has to do something, so it's a shared responsibility, and that involves configuring something on the service that introduces the new algorithm. A TLS configuration in elastic load balancing, or an SFTP configuration for transfer family. So these are shared responsibility. AWS brings the new algorithm in, but the customer has to enable the policy. And finally, there are other parts where the customer has to deal with it because it's not AWS's control, like source code or corporate firewalls that connect back to AWS. And these are not within AWS's control. So in a way, the shared responsibility model is complex on its own, right? Because there are many moving parts that have to be migrated or require some work from customers. So now let's talk about the pain points. So I have an example here where the architectural complexity introduces complexity for the migration. So I have AWS Amplify for writing an application for Android, and it does something. It has some logic and some UI. It was developed with AWS Amplify. AWS Amplify calls AWS SDKs underneath. SDKs are libraries or tools that enable to write applications that call into AWS services. So let's say that you use Amplify. Amplify uses the SDKs and calls to S3 to do something. Let's say update some images or something and store them in S3. And then the customer can use AWS Transfer Family to fetch these things that were stored and in order to process them, to do something else. So here we see the complexity of the architecture, a simple architecture, when it comes to migrating algorithms. So the first moving part is SDK. The SDK has to introduce the new algorithms in order to be used in AWS Amplify as you build your application. Now the SDKs use what we call common runtime, which is basic libraries that do cryptography and other things. So these libraries are the ones that have to enable the new algorithms in order to expose them in the SDK, in order for AWS Amplify to use them when you write the Android app. So they, basically the underlying crypto libraries have to be upgraded under the SDK. And then the S3 service has to do work in order to use the new algorithms for the transfers and also for the storage or whatever work that takes place in the service itself. And then the customer has to configure the right SFTP policy in order to be quantum resistant. The SFTP policy that enables MLChem, for example. And finally, something that AWS does not control, that's the client side, the OpenSSH client that connects back, or some Java SSH client or other clients that also have to support the new algorithms in order to make the whole the whole application quantum resistant. So that's the complexity that I'm trying to convey. The challenge is that in these complex architectures that we have, it's not as simple as migrating a library, right? There are so many things that some of them we control, some of them we don't. And it takes work. It can be challenging to say I'm end-to-end quantum resistant. I'll have a couple more here, and then I think we can go to Q&A. So AWS SDKs are building blocks for customers to write applications and interact with AWS services. And they, as you can see here, they're SDKs for many libraries. So another example I had to show the complexity of an SDK type of application was that we had a client application that was written with the SDK, and it calls back some HTTP request that goes through an API gateway to do something with API calls. And then from the API gateway, we call in a serverless Lambda function that does something else. So the client application calls an API, and the Lambda function wakes up. It uses Secrets Manager to get some secrets, and it uses the Python SDK to do something else, to store something somewhere or something else. So in this example here, let's see the moving parts again. We have the SDK, the HTTP requests that go through TLS. The SDK has the common runtime. So there is a set of libraries that have to be upgraded for this application to start calling to be quantum resistant. Then the RESTful API here, the gateway, the API gateway that is the proxy in the middle. The customer has to configure a policy that enables the new algorithms for these connections. So there's another moving part. And finally, here we have the other SDK that does something, and that SDK could be linking against OpenSSL for Boto3 for the Python SDK, right? So if OpenSSL here that comes shipping in the Lambda function is not the right version, then the customer would need to build a binary in the Lambda function itself in order to have the new algorithms. So that's something we documented, and in the future is going to be upgraded anyway. So you see here there is manual work here as well if it's early in the process before this is supported natively. So customers that want to migrate quickly, they have to do work in many places. And these are just some simple examples, right? They're more complicated examples. So architectural complexity of our use cases is a pain point that I was trying to show. And the last example I had, we talked about long-term software and as a challenge. We talked about architecture application complexity as a challenge. The last one is use case diversity as a challenge. So I teased that out by using the post-quantum certificate use case in the web and in the TLS connections to the cloud earlier. Now I'm going to dig a little deeper about the solution. So here's a pain point that I have been dealing with that hopefully is going to demonstrate that. AWS has TLS endpoints. These are the front ends to services that expose the functionality that the services have. So basically, the RESTful APIs that you call through TLS in order to do things with S3 or crypto or whatever service there is behind AWS. These TLS endpoints, they integrate with SDK applications written with SDKs, with browsers, and with third-party tools. So all of these connections go over TLS, and there are many clients, many types of clients that connect back. So let's talk about a potential solution that's called MTC certificates and how it affects or how it affects differently these use cases. So we talked about the endpoints. The endpoints, the TLS endpoints for AWS have to integrate with browsers because the browser goes to AWS console and you can configure the service like that, or SDK applications or third-party applications. We talked about that. Now, there's this new set of standards that are coming out of the IETF that are called Merkle tree certificates. This is a neat new solution for WebPKI. So it's good for the web and browsers and servers. And this is a draft specification here. And Merkle tree certificates are an innovative solution that tries to address the post-quantum certificate size that we talked about earlier. So Merkle tree certificates are much smaller. The 15 extra kilobytes that we talked about when we use post-quantum algorithms in typical X509 certificates, that problem is addressed with MTC certificates. So if the client is able to get updated frequently, every few hours, that means that Merkle tree certificates allow us to not transfer a lot of data. So that's a great advantage. Also, this is a great advantage if the connections are short and they don't transfer a lot of data, because if you transfer 100 megabytes, the post-quantum certificate size will not matter for the application. But if the connections are small and short, the Merkle tree certificate benefit is significant. And also, it's significant if the connection is slow. If you go from a mobile device where it's expensive to transfer 15 kilobytes, Merkle tree certificate offers a great advantage. So these are great advantages that we could reap the benefit of. But when we're talking about TLS endpoints, SDKs and third-party applications today that connect back to AWS services over TLS use certificates, of course, for authentication, but do not have this option of getting regularly updated. So this concept of fetching part of the Merkle tree certificate in order to reap the benefit of the size that we talked about earlier is not built in today. So these applications today, it would be hard to say that I'm going to start fetching the Merkle tree every 2 hours so I can reap the benefit of MTC. So that's a pain point for a solution because this doesn't exist. The functionality of getting updated that frequently does not really exist. Additionally, though, more importantly, because we could introduce that, let's say, more importantly, like we showed earlier, these TLS endpoint connections that we see, they're usually over fast networks. So 15 kilobytes is not too much to worry about. And also they transfer sizable amounts of data. So, that the 15 kilobytes for these connections would not be that noticeable. It may be 1 or 2 milliseconds slower on the application, but it would not be as significant as it would be for a web connection that transfers only 5 kilobytes. So MTC certificates are a little hard to integrate in SDK clients and third-party applications. It would require new infrastructure to be able to distribute these Merkle tree subtrees. And also the benefit is not huge because of the nature of the connections today. So the question would arise here, MTC is a great solution, especially for the web. Should we deploy it in TLS endpoints for SDK connections that go through SDKs? The answer is we have to deploy it because we have to integrate with browsers. So TLS endpoints integrate with browsers through the AWS console, and browsers will use MTC certificates because they're a great benefit for the web. But if it was just for the SDKs, right, the SDK applications that connect back to the TLS connections, it's questionable if the benefit would be worth the extra effort of introducing this new functionality. So the point is, we have two use cases. MTC is great for one use case. It will not benefit as much for the other use case. And if we had to choose between the two, we would deploy differently for each of them. But in the end, we're in a world where we have to integrate with many clients and we have to support both. But it is an argument to be made about the intricacies of each use case and the solution that gets deployed in each. Last slide that I had is talking about these types of certificates for private PKI, at least in the context that I have seen in my interactions with teams. So MTCs are great for the web. How about private PKI? So private PKI usually, the Merkle tree certificates use Merkle trees. We talked about that. They distribute subtrees to the verifiers in order to reap the benefit of the size. And they use cosigners in order to distribute trust to the clients. So MTC certificates are a great evolution of the WebPKI as we know it, because they address a bunch of problems, a bunch of challenges. But in the private PKI use cases, at least in the most common ones that I'm aware, the PKIs, they don't have a great number of root PKIs. In most common private PKI use cases, you don't have a lot of root CAs. They also don't have SCTs as we know them today. They don't have the transparency aspect that we have for the web PKI. So basically, there are less signatures in these certificates. So the sizes of the chains are not huge. They are slightly bigger, but they're not huge. Also, they don't have this concept of distributing content like from CAs. So it would require work to say, I'm going to start fetching parts of the Merkle tree in order to reap the benefit of Merkle tree certificates. So the most importantly, many of these use cases, the private PKI, they get a certificate and they need it quickly. There are applications that wake up in the data center, they have to open a connection, they get a quick certificate, they use it, and then they go to sleep. So for these types of application where the application wakes up and needs a certificate quickly, it's a little more challenging to do that with Merkle tree certificates because you need a little time for the certificate to propagate in the Merkle tree. So the client has to find out. So generally, I mean, there might be some private PKI use cases with where Merkle trees, are great, but in the ones that I'm aware of, there's another example of a great solution for WebPKI that does not lend itself easily for most of the private PKI use cases, at least the ones that I know. So it's another example of intricacy of the use case that defines a different solution as necessary. Um, so in closing, I think that's the last slide. In closing, the takeaway is that long-term support of applications can be a pain point. Library dependencies are a pain point. Standalone application migration is relatively more straightforward, especially if you carry your cryptography in the application. Swap and replace versus side by side is something that we need to bear in mind when we migrate. Architectural complexity is another pain point. And finally, use case characteristics introduce different needs or challenges for post-quantum migration solutions. And that's something we need to keep in mind. That's what I had. I think we have a little bit for questions. And thank you for listening.
Yes. Thank you so much, Panos. It was a really great talk. And we get some positive feedback already on LinkedIn, so thank you for that. I don't know, we have 3 minutes left to our official scheduling. I don't know if you have a few minutes more, but there's a couple of questions both in chat and Q&A box. So if you have some time, you're welcome to pick any of those up because you did cover some of them. They were coming in as you were speaking.
Yeah, let me check.
Mm-hmm.
I see some commands to find algorithms in an operating system. That's fine. What's the effect of on OS security in post-quantum? So I don't know what operating system security means generally, but operating systems use cryptography in a thousand ways. So generally speaking, they affect post-quantum cryptography, or the quantum computing risk affects operating systems greatly, like any other use case. Operating systems sign software, they verify software at boot time, they use encryption in the kernel level, they use encryption in connections, they use encryption at rest. So operating system security is greatly affected by post-quantum because it uses cryptography in many, many places. Let me find one more. I'm reading Agilos's question. Yeah, so Agilos is making the point, when we are evaluating uses of cryptography, he's using the example of TLS, should we be starting to look into the overhead, not on a per TLS connection basis, but on a TLS endpoint basis, and look at the connections that are short-lived or tail-heavy connections. So I think that's a better strategy. I think traditionally we had been looking at TLS handshake as an indication of performance, and it definitely is. But I think when we're digging deeper on the use case, the load on a per TLS endpoint, the tail heavy or the short-lived connections, how much data per connection, and how much application performance is affected by data is also important. I have looked into this before, and I have been advocating for looking at time to last byte as a better measure of application performance in this context instead of TLS handshake. But Agilos is right. I think looking into beyond TLS handshakes, looking into the endpoint itself, the nature of the connections, the data per connection, and how the tails and the percentiles move in this, in this context. I think that these are better indicators that we see. Another example could be resumption. If you're using a lot of TLS resumptions in these connections, if your resumptions are 80%, you will not sweat MLDSA too much. So it depends on the nature of these connections. I think Aggelos makes the right point to start looking into these metrics more. So the other question from Bijaya is, what if there is no algorithm in the operating system? Should we upgrade the OS or install the new algorithms? So that's the point that I was trying to make. Moving to a new OS that has the algorithms, of course, is an option. But this is not always straightforward, because when you pick an OS, you usually certify it or you get some sort of approval, and moving to a new OS requires process. Of course, that's a solution. Another solution is migrating the crypto library and the applications that link against it. So that's why I was talking OpenSSL side by side or swap and replace. And these are challenging sometimes. So that's what the idea that I was trying to make. You migrate your library or your application, but you need to remember that there are many other things that could be linking against the library. So you got to be careful as you're migrating. Let me see, is there another one? How do you discover the cryptography in the applications? Okay. Tomas, that's a new that's a new workshop. So this is the discovery discussion. There are many resources and companies that try to do discovery and tools and options. I think that would be a useful next webinar, Tomas. The discovery topic is it's a complicated and interesting topic.
Mm-hmm. Would be happy to do it, Panos.
As long as it's not me. Because it's a complicated topic.
Okay. Panos, I don't want to keep you too long. I think it's great, because you covered a lot of questions. But just to make sure, because we have some Q&A questions and so on, right? So if you have a couple of more minutes, feel free to answer them, but we can also wrap up. I see some people have dropped as well.
Yeah, I think I see one more from Vijaya. Robert was talking about CBOM, and there's no great solution for discovery. So there are vendors that focus on discovery. I think it's a fair assessment to say that the discovery aspect is complicated, and there are many things to discover, but there are solutions. So AWS has a couple of vendors that are working on this. If you email me, I can connect you to the people that work with these vendors. I'm not here to advocate for any vendors in this topic, but there are some vendors that integrate in AWS and do discovery, and we could connect you if you're interested in AWS Marketplace. But generally, these vendors, they usually discover, they look at connections, they look at data sometimes, they look at logs, and they try to build an inventory so that customers can start focusing on the use of cryptography in some places. Yeah, so there was another question about customers that want to implement PQC in AWS, and how do we talk about how do we support them in that endeavor. I'll connect you with the right people. There are some teams that specialize here, like customer-facing teams, so I can email someone, and you can connect with the right people to help your customer. The webinar question, Tomas, I think it's going to be available. If it's going to be available online.
Yes, absolutely. So, oh, I'm sorry, I must have missed that question. Yes, it's going to be available in our webinar library, and actually on YouTube, it's going to be available right after this session. So you're feel free to review it later. Okay, Panos, I don't want to keep you longer because it was such a great presentation, and thank you for doing that and for taking extra time to answer all the questions. Now, before we go, just a couple of other words. For people that are new to Post-Quantum Cryptography Alliance, please join our community, and there are many ways to get involved. And you can join our Discord channel, which I shared in the chat, and you will have it linked in the docs, attend our community meetings, and also subscribe to our mailing lists. Oops. Also, please check our community calendar. They're open to everybody. So if you'd like to get new updates on the projects, you can also join our technical advisory council, our outreach committee, and so on. You're also welcome to do that. And there's a calendar and the link to the calendar just over here. You're also welcome to join us. So AWS is one of our members, as well as Google, Cisco, IBM, the premier members, along with a lot of general and associate members. So if your organization interested into joining the Post-Quantum Cryptography Alliance, please contact us, and there's links available for this here as well. Now, before we go, thank you so much again, Panos, for this great talk, and thank you everybody for joining. Hopefully, we'll see you again, Panos, on the new webinars. It just came out, from this discussion, which was great to see. Or maybe one of your colleagues, if you think it's too complicated to get it through you. But either way, thank you so much, and thank you for presenting this great topic. And thanks again for everybody for joining. And see you next time.
Thank you, folks. Thanks so much.
Thank you, Panos.